Multi-head attention is the beating heart of every modern transformer model. From GPT-4 to DeepSeek to Gemini, this mechanism is what allows AI to understand context, relationships, and meaning across entire sequences of text. In this video, we will dive deep into exactly how it works, the query, key, and value matrices, the attention scores, the softmax operation, and why we need multiple heads. By the end, you will understand the complete mathematical flow and the intuition behind why this architecture has revolutionized artificial intelligence. Before diving into the mathematics, let's understand the core intuition. Imagine you are reading a sentence, "The cat sat on the mat because it was tired." When you process the word "it," you need to know what it refers to. Your brain automatically looks back and focuses attention on cat, not mat. This is exactly what attention does in neural networks. It allows each word, or token, to look at every other word in the sequence, decide which ones are most relevant, and blend their information together. The result is a context-aware representation where each token knows about the entire sequence. This is the breakthrough that made transformers possible, and why they outperform every previous architecture in natural language processing. Now let's understand the three matrices that make attention possible: query, key, and value. Think of it like a database search. When you want to find information, you write a query, what you are looking for. The database has keys, descriptions of what is stored. When your query matches a key, you get the corresponding value, the actual information. In transformers, every token produces all three: a query describing what it needs, a key describing what it offers, and a value containing its actual information. Each token's query is compared against all other tokens' keys. High similarity means high attention, that token's value will be important for understanding this token. This is implemented using learned linear projections, three separate weight matrices that transform the input embeddings into Q, K, and V matrices. Now we arrive at the heart of the attention mechanism, computing attention scores. Here is the complete formula: attention equals the softmax of query times key transpose, divided by the square root of the key dimension, all multiplied by value. Step by step, first, we multiply the query matrix by the transpose of the key matrix. This computes similarity scores, how much each token's query matches every other token's key. Second, we scale by dividing by the square root of the key dimension. This prevents the dot products from becoming too large, which would push the softmax into regions with extremely small gradients. Third, we apply softmax to normalize the scores into a probability distribution, all positive, all summing to 1. Finally, we multiply by the value matrix. This creates a weighted sum where each token receives information from other tokens proportional to their attention scores. The result is the context-aware output. Now we understand single attention, but why do we need multiple heads? The answer is that a single attention mechanism can only capture one type of relationship. But language is complex. Consider, the animal didn't cross the street because it was too tired. The word "it" could relate to animal, that's the meaning. But it also relates to street, that's the position. And it relates to tired, that's the state. Different heads learn to focus on different aspects. One head might track subject-verb relationships, another tracks pronoun references, another tracks positional patterns, and yet another tracks semantic categories. With 8, 16, or even 32 heads, the model can simultaneously capture many different types of relationships at once. Each head has its own query, key, and value weight matrices. They learn different projections that emphasize different aspects of the input. Let's see the complete end-to-end multi-head attention flow. Step 1. Input embeddings enter the module. Step 2. 3 linear projections create the query, key, and value matrices. Step 3. Each matrix is split logically across all attention heads. Step 4. Each head computes attention independently, Q times K transpose, scaled, softmax, multiplied by V. Step 5. The outputs from all heads are concatenated back together. Step 6. A final linear projection combines the head outputs into the final representation. This output has the same dimensions as the input, but now each token carries rich contextual information from the entire sequence. This is what enables transformers to understand long-range dependencies and complex relationships that previous architectures like RNNs and LSTMs could never capture effectively. Let's summarize the key insights. Multi-head attention enables parallel computation. All heads process simultaneously, making transformers highly parallelizable and perfect for GPU acceleration. It captures diverse relationships. Different heads learn different linguistic and semantic patterns. The scaled dot product prevents gradient vanishing, keeping training stable even in deep networks. Most importantly, attention creates global receptive fields. Every token can directly attend to every other token, regardless of distance. This solves the long-range dependency problem that plagued RNNs and LSTMs. Understanding multi-head attention is essential for understanding modern AI. It is the foundation of GPT, BERT, T5, and every major language model in use today.